Hi, class, are you there? Bushi Bushi, are you there?
Yeah.
Yes, ada.
Oh, thank you.
Yes, doctor.
Okay, thank you so much. Okay, thank you. So, oh, sorry, just now I missed some of the slide. That's why I just wondering why the equation so difficult. After we know, we need to refer to the chart. Actually, this one is the all unit 14 mil, and then PI lamination. PI means this one the type, or the type is like the core lamination, and then WTCU, TFE, MLT, MCL. This one, if you ask me, I also not very know that. Most important is you need to know how to apply this data, this table. Yeah, for example, we have three-phase standard lamination by using a Thomas Skinner 14 mil. And then, this one is something that those manufacturer already decide what is the value. For example, if let's say we want to design 0.5 EI, so what is the value for the D, for the E, for the F, something like this. They already decided. Same as well, if let's say we use a Thomas Skinner 14 mil instead of using this sample 14 mil. Actually, I also not very sure about that one. Sorry for that because I'm not good in here. And this book is quite old actually. We took it from a book actually. Transformer design calculation, the core geometry. So if let's say we want to calculate the core geometry, we use this equation. So where we get the WA, AC, KU, PT, KE, everything comes from the table, yeah. And then P total is input plus output, efficiency, or something like this. This one actually by right you need to memorize lah. This topic will be in the PBL. Yes, that's right. What is that? So for if let's say included the three-phase rectifier circuit, delta with the full wave, figure 12.11, I don't have it. So they calculated in EA, output. So if let's say we put it as electrical devices, if you pay attention on the phone part, we no longer say that instead as well for motor and also recently what is by using VA one, I forgot the recently one. And then this is put it in a circuits illustration. So this one is one thing of a phone charger. Inside here we have a one transformer, the second phone transformer. And then sorry, this one is not phone charger. This is three-phase transformer with a rectifier. But I think it will apply in other places. It's not phone charger. We have this type of a transformer. We also have this type of transformer. Depend on what we want to design. Yeah? We have a delta to delta. We have a delta to the Y. Either the other things. In the end, what we are interested is actually the input, the output, and sorry, input, and then output. Input, and output. Same as well. Here, input, output, input, output. And then we don't see what is the input here, what is the output here. No, because we see everything. It's like a network black box. What is the input? What is the output? What is the input for AC? What is the output for DC? Then primary turns, line current, phase current. In fact, this type of equation can be derived according to our previous study I mean from the chapter 1 until 5. But because of the table are in different scale, if you pay attention on that, This everything are in cm. This everything in centimeter square. This everything in a power of 4. This one is power of 5. Something like this. Need to be careful. So what we can do is we just directly plug and play. Plug and play. For example, you can ask me, Doctor, can we just ignore this one? By right, cannot. Okay, cannot. So can I use AC, for example, AC here? Can I use AC with a 1.5, let's say 1.532? Should I times 10 pi minus 4 to become meter square? Because since this is a centimeter cube, right? If let's say we convert to meter square, it becomes times 10 to the power 4 meter square. Should I do like this? Answer cannot. We just directly use this value. That's why it depends on you. And then the selection wire will be from the wire table. So later on, I'll show you the wire table. This is the wire table. American wire gauge. American wire gauge. And then we'll see what is the bare area, what is the resistance. If let's say heavy synthesized, synthetic, what is the charge? Later on, we'll go through the example. This one secondary turn, current, base current, secondary current. So when it state out like this, which means when we input all the value, all let's say after we do calculation, we have a 10, so it is centimeter square. For example, after we calculate if it's a 12, the m like this. Then our core losses by using this one. It depends on what type of material we are using on. And anything else? No more. Baru sampai dia punya kita panggil apa? Dia punya calculation. Let me show you the example. Okay. So just now we can you see my screen? Guys, can you see my screen or not? Does the wording too small?
Yes, doctor.
The
I
wording
can
too
see
small.
it very clearly.
Huh?
No, it's just good.
Boleh tengok tak? Oh, that's good. Okay, thank you.
Yes,
thank you.
yes.
Okay, thank you. So I just can only give you one example for this one. Then after that, you need to prepare your answer according PBL given their parameter. Then the PBL is more towards on calculation. Then so I think it will be easier for you guys. Maybe I'm not sure whether will you busy for this week and next week or not. Then because PBL1, you need to do and you need to do the calculation on time. After that time will be considered late. Because everything are given here, what you need to do is you will just input and do the calculation. Okay, design a three-phase isolation transformer. So for example, this one they give one code. Okay, so let's say what is the code that we have. Maybe later on. Oh, okay, I know. Okay. The code is here. Okay, so what is 1.5 EI three-phase? So have a look. 1.5 EI. Okay. This is the one we need to use. And then by calculating in the important parameters such as the core geometry, primary and secondary side winding phase turn, as well as the power losses, make sure the transformer can achieve the necessary efficiency. Actually, this one is required by the here. Okay. The design spec might comply. So input voltage 2083 wire, output must be 33 volt, and then 12 ampere, delta, full bridge, 50 hertz, regulation 7%, flux DAC is a 1.2. What is the material we have? then what is the window utilization, what is the diode voltage drop, and also what is the power density, watt per kilogram. So here we have a refer to the appendixes A and B. So this is the A. Okay, then another one is B. B is a American wire gauge value, wire paper. Later on, see this one first. So how to start the calculation solution? So for cogeometry of a delta delta, we need to use this equation, whereby I think it is here code, something here code, kg, something like this. In fact, there are a lot of equations. I didn't put it there. And then apparent power by using this equation, output power by using this equation. First of all, we need to calculate, substitute the output to calculate and get the output power. I out is 12, and then V out is 33, and then the voltage drop is 1.3, whereby 12 is here, 12 here, and then V out 33 at the top, and then anything else, then voltage drop is 1.3. So it's very easy, just direct plug and play. Then we found that the PL is like this. Then we substitute inside here. So we have a 427, and then equation 1.05, efficiency is 90%, then 1.05, then we get 947. Electrical condition KE also can be found from this one. Where is KE? KE is this one. KE is this one, yeah. And then what is that? 947 through KE alpha. So KE is calculated from here. Sorry, I stepped. 60 hertz. B is at the top by using how much? 1.2 is it? Yeah, 1.2. Okay. So this is 1.2. 50 hertz. Then we have a 1.03. Then substitute into KE. And then alpha is a 7%. Where is it? 7%. Where's alpha? This one. This is alpha. Huh? So everything is just substitute. Then we found this one. So from the primary side, by appendix A, this one, AC is here. So have a look. What is the value of AC? So AC, okay, 13.790. So 13.790 centimeter square. The primary turns using Faraday law. So we have a 208. Then BAC 1.2, AC is 13.79, F is a 50. So we have a 566 turns for primary winding. After that, primary current output divided by voltage. Then with the efficiency, we have a 0.76 ampere. Primary phase current, because this one is the line current. If you still remember, this is black box, right? If let's say we want to calculate the phase, then we divide by square root 3. Why? Because this is a delta delta. This is delta delta. So we divide by square root 3. And then what is the bare wire? The primary bare wire is by using the equation. So where we get this one? Sorry, maybe I stop here first. Got any problem or not? Do you have any problem? Hello? Do you have any problem? Wait, line tak ada.
No, sir. No, doctor.
No, Okay. So, KU. Oh, okay. Okay, thank you. Thank you is one. So, KU, where's KU? Silakan. AWP. AWP, where is it? Ada tak? Dah lupa lah. Ya, ada. AWS saja. Tak nampak AWP lagi. AWP. Tak nampak AWP ya. Mana dia? Oh, tak ada. Tak diberi ke? AWS ada. AWP. Kan tak beri AWP primary bare wire. Where is the primary? Oh, I think terdelete sini hilang terus. Terdelete kat sini. Okay, so by using the equation, we need to find Ku, Wa, and P. So from a specification, Ku is like this. At the same time, we usually assume Kup equals to Kus. And then we divide by 2 lah. So given is 0.6, so we divide by 2 is 0.3 lah. Therefore, the primary winding utilization is 0.3 from the appendix A. WA is this one. So have a look on appendix A. What is a WA? WA for this is 36.29. Okay, so 36.29. And then we substitute everything. Then we get this value. So from the wire table as shown in appendix B, the bare area is, okay, now the bare area of the wire, it should be something in this value. So we need to find which one is close to this value from the AWG. So AWG 20 is very close. So have a look at AWG 20. This one is AWG 20. They need to find very close value of how much? 4.81 times 10 to power minus 4.81 times 10 to power minus 3 centimeter square. So a centimeter square is here. 4.81 is about milli, right? This one is a 10. Inside is a 10 minus 10 to the power minus 3. So we need to find which is near to 4.81. So 5.188 is near to 4.81. So this is the value. And then we will use a bare area wire of this one. And then with the insulator, we pick up all the value. 5.188 is this one. And then what is the with insulator? So 6.065 where is that? 6.065. This is with insulator area with the insulator. And then resistance value. So what is that? 332.3. 332.3. The resistance value. Micro ohm per centimeter. So micro ohm per centimeter. So from appendix A, means lengthen, MLT means lengthen is 22 centimeter. So have a look. What is the MLT for this one? So MLT is 22. So MLT is 22. The primary resistance is like this. By using MLT times NP times this one means the resistance in here, then times 10 to the power minus 6. So this equation, where can we get it from here as well? Yeah? RP, this one, yeah. This one. This one. After that, total, then we have a RP. Total copper losses using equation to calculate. Then for secondary side, use equation, substitute, then find again. I think sini I'll go fast Substitute only. Same as well, using winding factor, and then using the equation, we calculate what is the centimeter required, and then which one is closer to this value, so we find it, and then we see the, then apply the data sheet, copy, calculate the RS, then find again. So this is the secondary copper losses. After that, the regulation, we can find the power losses according to transfer regulation. Then for the specification, nominal is 1.21 watt per kilogram from appendix A. WTFE and gram is we put it in a kilogram, so we have 8.42 in core losses, so we can find the total transformer losses. After that, what is that? After that, no more. No more. So when we find the transformer losses, we also need to know what is the efficiency because why I say so we need to know whether it is occupied the compliances the efficiency that required by the client or not. I think that I cannot teach you on how to derive all the equation. In fact, the equation are there. So what you can do is you need to do your own calculation, find your own wire, and do all the justification. So this is the PBL lah. Up to now, okay or not? Huh? Up to now, okay? Up to now, okay or not? Oh, okay. Thank you. So I just only have one example. I believe that is it very easy? We just apply the equation, right? No problem, right? Is this suit you? Guys, is this suit you? Uh, okay, I will just go on for the next question. This is for the electrical machine design to design a permanent magnet machine. So given the 12 slot 10 p.m. Brunson motor rotated at a 60 Hertz, assume that the number of turns per phase is 180 and the flux equals is 0.4 millivapor. What we need to do is we need to estimate the fundamental component of RMS voltage. For the phase back EMF, please refer the pitch factor and dissipation factor. And also we need to estimate the motor output torque. This pitch factor and dissipation factor are given, yeah? The solution. First of all, we calculate the pole pair, and then we just want to know the fundamental, which n equals to 1. So we substitute Kp1, Kd1, and then we find Kw1. So given the total is like this, we want to find the RMS value. So by using this equation, so we know the F is a 60 Hertz, Kwn is here, given, then given. So we just substitute, then we find this value. Then given the peak sinusoidal is a 12 ampere, so normally operated at the unity power factor, we use this equation on. EM top. Yeah, we use this equation, but this one is not correct. We cannot use this omega m to do the calculation. So formula something wrong. That's why calculation is wrong. I will update this one. I will update this one. So this similar question will come out in the final exam. This one. This one will come out in final exam. I will share with you this one. I will share with you. Whereby this is the things that requested from the feedback by discussing the similar question. But I cannot give you the same question or else I will die. It's something similar. So okay. So any question from you guys? Finish this chapter already finished? Very fast, man. So I will not repeat solution on the example 1 and 2. In fact, I already give you one example. So what you can do is you need to do it yourself for the next problem-based learning. I think the PBL will be released next week, not now. And then you need to finish it within 1 week, submit on time. Because it's not that difficult, easy. So, and it is individual. You need to finish by yourself. So, okay. Any question?
No, Doctor.
No?